Welcome CTM students to the lesson for 13.7. We're going to talk about, in this lesson, different types of distributions and mostly about normal or Gaussian distributions. We're going to check those out and find out what Z-scores are and how to use a Z-table. That's the biggest things that we'll be looking at here in this lesson. So 13.7, here we go. I want to start off by just looking at some common distribution types. We're just going to draw some sketches for right now. So these don't have to be real nice and neat. Try to draw them as neat as you can, but just freehand is fine for this. So one type of distribution you might see, and these will all be plotted as histograms. So a little review from what we've been doing in the past for this chapter. A rectangular distribution might look something like this. So here is your scores, or your data values on this axis. This is your frequency, always on the y-axis, and a rectangular one would be where they're all the same. So perhaps the chance of rolling each number on a six-sided die, you could have something like that maybe. I'll draw 6 of them in here. So this would be the chance of rolling a 1, 2, 3, 4, 5, and 6. It could be something like that. And then in red or in a different color, whatever color you're choosing to use, I want you to outline some things or add some things into the pictures. This is why this is called rectangular, because it looks like a rectangle. Imagine that. Amazing. Okay, so let's move on to a different one, a little more interesting, I think. J-shaped distributions. There's a couple different ways you could see that. So a J-shaped, it goes down continuously at kind of a equal intervals or something like that, you might say, or at the same slope. And so J-shape looks something like this. That would be a downward J-shape, and then an upward J-shape. It wouldn't have to be exactly all the same drops. It might be a little bit less, but the general trend here is a J-shape or a backwards J-shape. And so you might have something like this. This goes with both of these here. It could be going up instead. So nothing's coming to mind right now as to what might be in this sort of shape. Maybe it's it could be like that. Maybe the population of a country, as you get older and older, people are going to start dying off. Kind of a morbid example, I guess, of that. But there's kind of this J shape here. It follows that pattern. Think of that as a backwards or reflected J. This is more what we're used to. So think of this kind of being a J shape. If you put a dot right there, it'd be it's not a perfect J, but that's why we call it a J shape, because it kind of holds there. So yeah, maybe as people get older, they die off. This is the number of 50-year-old people living 60s, 70s, 80s, and 90s, something like that. It could be something to that effect. You might have that going backwards as well. Bimodal. Bimodal just means two modes, and so you're going to have two values showing up the most, and then the other ones could be kind of anywhere, but there's two that definitely stand out. Bimodal, you have something like this, and then boom, there's another one that's way up there, same level, and you've got these other ones here. So bimodal, what makes it bimodal? You have two modes. So some common ones here. Maybe there's two things that are most popular, two choices that are most popular in a survey, something like that. You could have bimodal based on that. Skewed, you could have a graph that is skewed to the right. So I want to make mine a little bit longer here, actually. Or skewed to the left. And so when we're saying skewed to one direction or another direction, it kind of has a tail. I want you to think of the tail as the skewed part. So here, if that goes up there, and then all of a sudden it starts coming back down. So this is just an example, but here's the tail of it. You think it kind of gradually gets going down there. Think of that as the tail. So this is one that is skewed to the right, and then I'm just going to take this and basically reflect it. It won't be a perfect reflection, but imagine something like this, and then it starts going up a little quicker, gets higher. You don't have to have the same exact number of bars as I do, but that one would be more skewed to the left because the tail is going to the left here. And so I want you in your different color to draw something like this, and notice how this one kind of goes down like that, and this one is the same sort of thing as that, but just reflected the other way. So this one is skewed. This one is skewed to the right over here, and this one is skewed to the left. So this is the tail part here, this is the tail part here. The way the tail is going is the way that it is skewed. And then the most important one for us, the one that you see most often, is a normal distribution. So a normal, it's kind of like it sounds, to me at least. Normal is kind of, this seems more like a normal way to distribute data. So half of the data is down here, half of it's going to be over here, and things rise, meets right at the middle there, and everything's symmetrical. So notice this is the same as this bar is the same as this bar, and so on. A lot of things in everyday life that we come across are distributed this way. So sometimes test scores or IQ scores, quite often they're distributed this way. A lot of times things that get manufactured, there'll be a lot of defect or a smaller number of defective products here, and then the lifespan of something could be like this. There's all kinds of different things that we might see. So let's give that a label, that this was normal, a normal curve. It's a normal distribution, or sometimes we refer to it as Gaussian, named after a famous mathematician, Carl Friedrich Gauss. Yeah, he lived, when did he live? Just out of curiosity. I don't know if it says right there. No, I'm not sure when he lived, but it was a little while back. I think at least 100, 200, maybe even more years ago. Bad history today here, Mr. Wagner. Can you give us more specifics? No, look it up. Type it in. You're watching this online, right? Type it in. You can find out more about Gauss. He's a pretty cool mathematician, though. Legend has it that he was able to, as like an elementary school student, he added up the digits 1 through 100 in his head in like just a matter of seconds, and said it was 5,050. But he thought of a clever trick for that, and from that day forward, the legend has it that he kind of became this math savant and just was a brilliant mathematician from that day forward. But Z-score formula anyways. The Z-score. How do we find a Z-score? If you've taken a statistics course before, you remember this from a previous math class. This might look familiar, but it's as simple as this. The data value, take whatever you have for your data value, subtract the mean from that, and divide all that by the standard deviation. And now a formulaic way, and using symbols to write this, would be x minus, and now we're going to use that mu symbol, the Greek letter, instead of x bar, and here we're going to use sigma instead of s, because we're talking about the entire population now instead. So I want to make a note of that right here. Let's circle that part. That's the key thing to remember for much of this lesson, is that formula right there, and this is what it stands for, or that's what it means. So let's write this off to the side though in a different color. We're using the mean as the mu and standard deviation as sigma instead of s and x bar. So I'll put and not x bar for the mean and s, because b/c, because we're talking about the entire population. So this formula is going to be critical for us as we continue looking at this lesson. So first of all, let's just calculate some z-scores. Let's start with that, and then we're going to use a Ztable to figure out some more interesting stuff about a set of data or a certain type of situation. Okay, so here's what we're going to do for example 1. A normal distribution has a mean of 60 and standard deviation, which I'm abbreviating like that, of 5. So that is a measure of the spread, remember, a measure of the spread of the data. How far is this data spread out? We're going to find the z-scores. And if you're finding z-scores, that's always going with normal distributions. You can't find z-scores unless something is normally distributed. So find the z-scores for values of, and we're going to look at some different parts here. So let's say we start with 65. How could we find the z-score for that? So I'm just going to say for 65, let's do this. We're going to use this formula right here. So use x minus the mean over the standard deviation. I'm not going to write that every single time. I'm just going to write that one more time here so we see that one more time. So how do I figure this out? Well, my value, the x value, gets replaced with 65. That's the value, the data value. The mean, it says right up here, is 60. So we have 60 over the standard deviation is 5. So this would be a pretty simple one. Very straightforward. You'd have 5 over 5, which equals 1. And that would be it. That would be your z-score. We're going to use z-scores in the second example to figure out some, what I think is a lot more interesting stuff about a situation, about some test scores that we'll look at later on. So z here equals, I'm just going to plug it in. I'm not going to rewrite this in the general way. I'm just going to plug the values in. 71 minus 60, your data value, minus the mean, over 5. That would be 11 over 5, which would be 2.2. I was almost going to say 0.1, but that would be 2 1/5, or 2.2. Part C, if you had 60, let's say, that would be a z-score of, and notice I'm putting a little dash through my z so it doesn't look like a 2. I would highly recommend you do the same thing. You got 60 minus 60 over 5. This would be 0 over 5. Can you have a z-score of 0? Sure. That actually just means it's the same value as the mean. So the z-score of 0 would mean that you have the same value as the mean to start. And then 53, this would be below the mean. So you should expect to have, when you have something below the mean, you should expect to have a negative value. And that's exactly what we're going to get here. 53 minus 60 over 5, that's negative 7 over 5. That's negative 1 2/5, or as a decimal, negative 1.4. Alright, let's put this in a different color. I want to make some notes about these things. That right here, 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 and here. These are the number of standard deviations above. If it's positive, it's above the mean, or below if it's negative. So this one would be negative or below the mean. These two would be positive, above the mean. This one's 0, so it's right on the mean. Okay, so that's what those numbers are referring to, or what it's saying about that. So pretty far away from the mean here, 2.2 standard deviations. This is just 1, this is right on it, and this is negative 1.4 in the opposite direction, in other words, away from that. Now here is a z-table. At first, you're going to look at this and be like, what the heck is going on here? We're going to use this z-table to figure out the percent chance of certain things happening, or how many percent of the population maybe is included in within a certain standard deviation or 2 standard deviations or whatever standard deviations of the specific value in question, or how many of the people or whatever we're looking at lie in a certain range. We can use Ztables to figure that out. So right now, don't worry about this. We're going to come back to this though as we do our second example, and it'll make a lot more sense within the context of that example. So let's pretend that we're going to look at some Cassie scores. So the California high school exit exam, currently at least as the date I'm making this video, it's an exam that all sophomores have to take. If you don't pass it as a sophomore, you get a chance to retake it in math and English, and you have to pass it in order to get your high school diploma in the state of California. So let's say that this is the situation. Suppose a certain test, we're going to say it's the Cassie, but it's not going to perfectly line up with it. I'm not actually sure if the Cassie scores are normally distributed, but we're going to assume they are right at about the proficient mark, which is about 380 most of the time. When you're taking the Cassie, a 380 is proficient. So it has normally distributed scores with a mean of 380. 350 is passing. So we'll say though that the mean is the proficient mark, 380. Where they came up with these being passing and proficient and advanced and stuff like that, I'm not really sure. I don't know why the numbers are the way they are, but that's how they did the scoring. So in a standard deviation of 30. Is this actually true of all Cassie scores, that the standard deviation is 30 and the mean is 380? I don't know, but I feel like it's pretty close to that. I've taught Cassie math in the past before, and to me it seems like that's the norm. Right about proficient is pretty normal. So find the percent of individuals with test scores, and we're going to have some different parts to this. So multiple parts. Part A. This will be the last example we do, but it's going to be a number of parts here to look at, because each part will kind of give a little new twist to something. We're going to cover all the different variations you might see with problems like this. So between 380 and 410. So first of all, we need to think of what are their z-scores. Once we know their z-scores, then we can use this table to figure out what the actual percentage of people is that would be scoring between 380 and 410. That's the beauty of the z-table. Once you figure out the z-scores, you can use those z-scores to figure out or calculate the area. From here it's saying the area here to here is whatever the z-score is. You find that, and you find, as long as you know the mean, this is how far that is from the mean. The z-score is how far it is standard deviation wise from the mean. That will give you the area under the bell curve, under the normal distribution curve right there. So let's figure this out. So 380, what is the z-score for 380? For each value that we have, we'll put a lowercase z and then a subscript of the number. So a z-score for 380 in this case is, we're going to use our value minus the mean over the standard deviation. So 380 is the value, and it's also the mean. In this case, over the standard deviation is 30. That'd be 0 over 30, which would equal 0. Pretty important. I'll circle it. Not a final answer though, so I'm not boxing it yet. And then z of 410, that's 410 minus 380 over 30. You would have 30 over 30, which would be 1. So a standard deviation of 1. This is right on the mean. This is 1 standard deviation away from the mean. And then from here, I want you to draw a graph. This is something you might not have to do once you get the hang of it later, but the graph is going to help us visually see what's going on. So I want you to draw your best, it's not my best work there, but I think that will suffice. That'll be good. So your best normal curve. Some normal curves are a little steeper, some are a little more flattened out, but a normal curve, it's just got half the data here and half the data over here. It curves up, and it's normally distributed. It's symmetric as well. So if you drew the mean, which I'm going to do right now, find the very tip-top point, the very maximum point there, come down from there. Let's come down with a hidden line, and we're going to come down about to here too, so match it up with yours. We're going to say this was my score of 380, which is the mean, which should be the very middle point right there if it's normally distributed, and this is going to be my score of 410. So these are my original scores right here, and these are my z-scores right underneath it. So I'm going to write the z-scores underneath it there. Why don't we do the z-scores in the different color? That'll be a good way to keep these a little easier to read, I think, or a little easier to look at and pick out the important information later on when you use these to help you with classwork and studying. So 0 right there, that's a z-score of 1 right there. What we're trying to figure out is this area right here. And so let's shade that in with our different color. This is what we're looking at. We're trying to figure out what's that area right there. And so the area of this, get out my normal color again, this area is based on the z-table. We can figure this out. So from the mean, one standard deviation away. Let's go back to the z-table. This is not a table you're going to have to memorize. Don't worry about that. I will give you something like that on the test. I'll give you a z-table just looking like this, or looking just like this. Let's figure this out. So right at 0, there's no data above or below the mean right at 0. But from a z-score with a z-score of 1, that's right here. The z-score of 1 is the same as 1.00. So it's supposed to have 34, this would be 0.341, or 34.1% of the data lies in that area. So this is saying your mean, which for us was 380, and your z-score, we had 410, the z-scores were 0 and 1. So we're saying between here and here, between 0 and 1, you have one standard deviation away, 34.1% of the data lies in there. I'm going to get rid of all that stuff and put it on, or put it with the actual problem here. So the area of that is 0.341, which is the same. It says find the percent, so I need to change this to a percent. Find that as a percent, moving the decimal 2 places, gives that to you 34.1%. Okay, we're going to do a few more parts here because there's different twists that you're going to see. So here's a new twist. Let's say between 340 and 380. So if you're thinking about things as we take notes here, like you should be, like you always should be, and not just mindlessly copying things down, but thinking about it, you should be thinking, hey, that's going to give me a negative value, but I didn't see any negative values for the z-table here, so how can I work that out? Hold on, hold your horses, hold the phone, hold everything. Let's see, we have 340, that's the data value, minus the mean value, over the standard deviation. This would equal negative 40 over 30, which would be negative, approximately rounded off, because we're going to use 2 decimal places in the z-table. It's approximately negative 1.33. That's negative 4/3. You can reduce that. That'd be negative 1 1/3, which would be negative 1.3 repeating, which would be that rounded off. And so that's z of 340. We still need z of 380, but we already know what that was from part A. We already figured that out, so I see no need to rewrite the same numbers again. I'm just going to say it's 0. I already know that from part A. So write down from part A. So let's draw another graph here. And yes, I want you to draw all the graphs for this one. Later on you might be able to do these things without drawing the graphs. You might be able to just look at the z-table and figure it out from there. But this is your mean, so we're always putting in the mean value. And then we're going back now 1.33 standard deviations. So I'm going to make it a little wider than this because that was just one standard deviation. So back just a little bit more than that. We'll say that's about right there. This is 340. These are your original scores right here. We'll put the z-scores underneath it. So this is a z-score of 0, and this is a z-score of negative 1.33. So I'm trying to figure out what's the values in between there. What's those values right there? What's that area right there? So this would be, this area would be equal to, well, think of it this way. If you had, since it's symmetric, if you had 1.33 over here and you drew a little line there and figured out that area, that has to be the same as this one. That's the thought process here. So negative 1.33 is going to be the same as positive 1.33 because it's symmetric. So go back to the z-table. Let's find what the value is for 1.33. There it is. It's 0.408, meaning that 40.8% of the data of the scores lies in this range. So this would be 0.408, or as a percent, 40.8%. And let's just write why we could do that again. So since the area for z-scores of 0 to 1.33 is the same as the area of z-scores of negative 1.33 to 0. Why was that? It's because normal curves are symmetric about the mean. So if you have negative z-scores, just think of their positive values and the area would be the same. So area is always a positive value. You're never going to have a negative area. That's just crazy. That's just cray-cray. This is what we need right there. Okay, good to go. Yeah, I'm going to put this on a new page. I just don't want to try to squish it in here, so I'm going to keep going on a new page here. Let's say part C. Now between a new little twist here again, between 340 and 410. These numbers should look familiar. We've already found the z-scores for 340 and for 410, right here and right here. So we don't need to actually calculate the z-scores again. We can just say that z of 340, just as a reminder, was equal to negative 1.33. We figured that out in part B, so let's say from part B. And there we go. And z of 410 was equal to 1. So we're going to be using that and that. This was from part A. So time to draw another graph. Another normal curve. Put in the mean right in the middle. Always going to put in that mean value. That's 380, and then go back. So I'm trying to just copy this and try to make things the same width as they were before. This one's a little bit skinnier because it's not quite as far out. This is 410. This is 340. These were the original values, and then those translated into z-scores using the z-score formula. The z-scores were 1, 0 here, and negative 1.33. And we already figured out the area of this one. This one we know was 0.408. So let's write that in right there. This one we knew was 0.341. And so now we're saying between 340 and 410 would include all of that. So let's shade all of that in here and over here. What are we going to be doing to find the area, or to find all the values from here to there total? We're just going to add these two together. It's as simple as that. So the area of the whole thing, the whole shaded part, is going to equal 0.0 or 0.408 plus 0.341. That is equal to 0.749, which is the same thing as 74.9%. And a couple more twists here. 3 more twists actually, and we'll be calling it a day from there. So between 410 and 430. We know 410 already. We figured that one out long ago in part A. This was equal to 1. So this is still from part A. And how about Z of 430? You have not figured that one out yet. So 430, data value minus mean value, minus 380 over standard deviation is 30. We have 50 over 30. That's 1 2/3. Rounded off, I'll put approximately equal to 1.67 now. So that is what we're going to use for that Z-score. So between there and there, let's draw another graph. Put in the mean. This is 380. 410 is 1 standard deviation away, so 410 is about right there. And then 430, it's about 2/3 of a standard deviation, so this should be about 2/3 the width as this one is, as best you can. Just sketch that in. Here's my original values, and then the Z-scores. The Z values are here. This is a Z value of 0, 1, and 1.67 approximately. The area we want is this area right here, from 410 to 430. So let's shade that in a different color. We know that this, based on what we just talked about in this one, we know this is 0.341. We knew that actually from part A. So I'm going to write that in right here, but I'm not going to shade this in because I don't want to count this part. So we know this is 341, that area right here, but how are we going to calculate what this is right here? We know from here to here, how far is this? Let's put that in right here. So from here to here, from 380 to 430, or more importantly, in other words, from 0 to 1.67, what percent of the data lies in that range? So go back to your Z-table, from 1 to 1.67, from 0 to 1.67, that's what we need to figure out first. That would include 45.3% of the data, 0.453. And so that's saying something like this, the whole thing, but we want to get rid of this part. We don't want that part, we just want this part right here. So we're going to take this value, one more there, okay, this was 45.3% or 0.453, okay? So for the area from here to here, if I were to shade in the whole thing, that would be 0.453. So if I take this one and I subtract this part, I will be left with this part. That's how I'm going to figure out what the area of that shaded part is. So the area is going to equal, well, let's actually write a little bit of commentary before that. So since 34.1% of the scores are between B/W, between 380 and 410, and 45.3%, let's circle that down here too. That's my two most important numbers here to be able to figure that one out there. Since 45.3% are between 380 and 430, it follows that 45.3 minus 34.1, that would be 11.2% That is my answer. 11.2% of the scores are between 410 and 430. It was just a matter of finding the area of the whole thing, subtracting the area of this part to get the leftover area right here. And two more twists. Let's say we have part E below 440. So pretty high score there. 440 would be an excellent score on the Cassie. Z of 440, you're going to be, well, let's see, how many standard deviations away from the mean is that? How many standard deviations above the mean, more specifically, is that? So we have 440 minus 380 over 30. That's 60 over 30, which is 2 standard deviations away. It's pretty far away, especially if it's a normally distributed thing like this. That's going to be a very good score. You're going to be in a high percentile category. This would be the mean again, 380. And we're going, 1 was about here, we were saying, so I'm going to go out to about here. Notice already below 440, that's going to be most of the values. So it'd be everything over here, including everything down to here. This approaches the line, never actually touches technically. It's kind of like well, you learned about asymptotes in your algebra classes, algebra 2 especially, when you did conic sections like hyperbolas and not parabolas, but hyperbolas. Oh, what else? I think that's what's coming to mind right now. Hyperbolas, you had asymptotes. Things you couldn't actually touch, but you got closer and closer to. So we've got 380, 440. We're saying what's the area of everything over here. We know the area of this part from here, everything included over there, has to be 50%. So this time I'm going to write percent instead of the decimal values. It's fine to write it like that. It's fine to write it the other way too. But why is this the case? This is always true. It's always true that 50% or half of the data is below the mean for normal curves. That's why I can just assume that without even looking at any values in the tables. So this is a z-value of 0. That one is of 2. These are my original scores again, and these are my z-scores down here. So this is 50%. This would keep going this way, but it keeps getting smaller and smaller and closer to the axis. This is 50%, this part over here. And I also want to add to that this part over here. So I'm going to be saying everything below 440. So from here on over, this is the only little part, the little chunk right here, and it keeps going on and on, but this is the only part that's not included in the shaded part in what I want. Below 440, the area of this from 0 to 2. Now we have to go back to our Ztable to figure that out. So the area based on a z-score from 0 to 2, that includes, so here's 2, where's 2? 2.00. That's going to include 47.7% of the data. 47.7% of the data will be from the mean to that value. From the table, directly it's that decimal, which is the same as 47.7%. So this is not a final answer, but we're real close now. So this value added to the 50% for everything below the mean, you would have, we could say therefore, yeah, therefore symbol. Man, I like that symbol. So quick and easy. Total percent below 440 is you take your 50 plus 47.7 and you have your answer of 97.7% of the data. So that means if this were actually normally distributed in the way that I said it was, that 97.7% of students would score below a 440 on the Cassie. And I think that's actually pretty accurate. It's really hard to get, for most students, hard to get above 440. 450 is generally thought of as it is a perfect score on the Cassie. And then part F, one last twist, one last little variation on this, trying to show you every variation that might happen to you just within the context of this one example. So, or this second example. So above 425.5, we'll say. So we would need to find the z-score for 425.5. So a z and then a subscript 425.5 written lower there. We have this minus 380 over 30. This minus 380 would be 45.5. And if you type that into a calculator, you get approximately 1.52. So this is my z-score. I'm going to draw one more graph. So this keeps getting closer and closer to that line there. This would be 380 again. It's your mean value. And then 425.5, here's about 1 standard deviation, so about half more of that, say is right about there. 425.5. These are my original scores and translated to z-scores, 0 and 1.52. What we're trying to find is everything above this. So we're trying to find now, shade this part in. We're trying to find everything here and above. How could we figure that out? Well, we know, let's also put this in, we know from here on up, this never actually ends, so it keeps going. So I'm just going to say from here to there, you have 50% of the data is above the mean. So what's the area of this little part going to be? Well, if we knew the area of this part from 380 to 425 and just subtracted that from 50, that would give me this leftover part. That's exactly what we're going to do. So the area of this part is going to be, we're going to take 50 minus, well, what is that according to the z-table? This would be minus, and we'll write that part in right here. Going way back, there we go. Let's clear those. So, there we go. Clearing the annotations here and finding a z-value of 1.52. There it is, 1.52. That would be 43.6% of the data would fall between, or in this range, from 380 to 425.5. So let's put a 43.6 in there. That's the area of that part. And now we're going to take 50 and subtract that. That gives me this part as my final answer. So 43.6, this would be 6.4%. And that'll do it for us. I'm not going to do another example like that because essentially this was 6 examples in one. 6 little mini parts in, not even that many, 6 parts in one. So if you got that stuff, you really should be able to understand these kinds of questions. But let me know in class if you had any questions beyond what we did there, and hope you do well on the classwork.